we are going to relook at, or take a second look at the first derivative test, and we're going to see how we can use this for maximization and minimization problems. We've already kind of done this, but we're going to talk a little bit more about what this gets us. So just a review here, looking at this, reminder that if the derivative is greater than 0 for everything on the left side and less than 0 for everything on the right, we have an absolute max. So for A, if we have a function with an absolute max, if you think about it, what's the derivative doing over here on the left side? The derivative's positive. What's the derivative over here on the right side? The derivative is negative. So that makes sense that that would be an absolute maximum. And then likewise for B, if we have a minimum, then we have it's decreasing to begin with, increasing, so derivative is negative, and it changes to positive. So now we're going to take a look at how this helps us and what this does for us here with our first example. All right, we kind of learned back in probably 6th or 7th grade how to maximize an area for a rectangle and minimize perimeter. And you probably found, not by doing calculus, not by doing algebra necessarily, but just by exploring, you more than likely found that the dimensions that always get you the most amount of area and the least amount of perimeter are squares. So I've chosen 2 problems here. The first 2 examples are things that should just be inherent. We should just accept them already with all that we've done with our mathematical career, but we're going to use calculus to in a sense, prove it. So if we take a look at this, we are told that we have a rectangle with an area of 625 meters squared. We are going to assume we don't know that the smallest possible perimeter would come from a square. We're going to assume that we don't know that. So our basic generic formula is just going to be A of x, the area, with respect to x, is going to be some length times some width. And maybe you want to go ahead and draw yourself that picture like we've talked about. So we have x and we have y. So we have a length and a width, and we are assuming at the beginning that they're different, this generic rectangle. Okay, so we have our area formula. We are trying to show that, or trying to minimize the perimeter. So our perimeter, and this should look very similar to section 4.1, the things that we did there. The perimeter is going to be 2x's plus 2y's using our perimeter formula. But again, if you notice, I've written this in terms of x. We don't want this in terms of y's. So we're going to have to do some substitution. Since we were given that the area formula, or the actual area is 625 meters squared, and we know that that is found by xy, we can solve this for y very easily, and then we'll use some substitution here. So if I solve this for y, I'm simply going to divide both sides by x, and I have that y equals 625 divided by x. Now I'm going to go ahead and I'm going to take this and I'm going to put it in this function in place of y, so that I have the perimeter in terms of x. So I'll have my 2x's are fine, but now I'm going to go ahead and write 2 times 625 over x. I want to go ahead and simplify this down a little bit further since we can, and I'll get 2x plus 1250 over x. And since we're also going to be taking the derivative of this, I want to simplify it yet even further. I would prefer not to use the quotient rule. So I'm going to move that x up to the numerator by giving it a negative exponent. All right, so we are ready to take the derivative. I'm going to go ahead and just slide everything up here, and we're going to find p prime of x. Remember, taking the derivative is going to help us find that critical point, one of the critical points, which then will be a maximum or a minimum in this case. So the derivative of the first term we know is 2. The second term is bring down that negative 1. You get negative 1250 x to the negative 2. And I'm going to go ahead and rewrite that so that I no longer have the negative exponent since I'm done taking the derivative. And I get 1250 over x squared. So that is my derivative. That is my p prime. Now we want to use the first derivative test, and we want to look at where is p prime. So where is p prime of x less than 0? We need to figure out where that is going to be, and we also need to figure out where p prime is greater than 0, but we'll start with less than. So I'm going to start with 2 minus 1250 over x squared is less than 0. And if you go ahead and add to, or I guess I added this to both sides, and then multiplied by x squared and divided by 2. So we end up with, let's see, it'd be x squared is less than 625. And if I square root that, I get the absolute value of x is less than 25. So that means that I'm going to be less than 25, which is exactly what I wanted. If you refer back to part B of the first derivative test, we want x to be less than all the c's when f prime is less than 0. And likewise, if I would set p prime of x greater than 0, then I would have the exact same scenario. And again, I'm going to go ahead and add 1250 over x squared to both sides, multiply by x squared, divide by 2, and end up with x squared is greater than 625. And if I square root that, I end up, or if I solve for x, I guess, I end up with the absolute value of x is greater than 25. So therefore, again, that fits part B of the first derivative test, because when f prime is greater than 0, all the x's are greater than the c's on that interval. Okay, so now that we've done that, we're ready to finish. We can go ahead. We now know that when we find p prime set it equal to 0, that we are indeed going to have the absolute minimum. So I'm going to go ahead and slide this up one more time here, and let's just set p prime equal to 0 this time. So we're going to solve it very similarly to what we were doing with the absolute values. I'm going to go ahead and move the 1250 over x squared to the other side to keep it positive. I'm going to multiply both sides by x squared. I'm going to divide both sides by 2, getting me 625. And when I square root that, I get x is plus or minus 25. Obviously, we aren't going to have a negative distance, so we know that this must be 25. And if x is 25 and we plug that back into our original equation, well, then we know that y also has to equal 25. And that just proved that the square, in this case, would be the smallest possible perimeter. All right, just like in the last problem, this time, we're dealing with a rectangle, and we're going to deal with a maximization problem. We're going to maximize the area, get the largest area possible. And again, this is very similar to the last problem. We already know that a square would get us the largest area for the least amount of perimeter. So we know that we're going to end up with a square. But let's go ahead and show how we can get this with calculus. So like the last problem, we have a rectangle. One side I'm going to call x, one side I'm going to call y. I know that the perimeter, which is found by 2x plus 2y, is 324. And I know that the area formula is going to be, sorry, I'm having issues with my stylus, is going to be xy. All right, again, we can't have the area in terms of x and y, only in terms of x is what we want, so we're going to solve this one here for y. And if I do that and divide everything by 2 and then subtract x from both sides, I get 162 minus x. All right, I'm going to replace the y in the area formula with what we found, y to equal in terms of x. So it'll be x times 162 minus x. And I'm going to go ahead and simplify that because I know I want to take the derivative, and I'd rather not do the product rule. Since it's easy enough to do this one without, I'm going to distribute the x. And I'm going to go ahead and find the derivative, because in order to use the first derivative test, I have to know where a prime stands over the interval. So a prime would be 162 minus 2x. All right. Using the first derivative test, part A, we want to know, in order to use it, we have to show that when f prime is greater than 0, we have to show that x is less than c. Whereas in the last problem, we showed that when f prime was greater than 0, x was greater than c. So this is easy enough to do with 162 minus 2x. We're going to set that greater than 0. And, just a note here, I guess, is that f prime is the way the first derivative test is written, but really we're using a prime in this case, so this could be translated into a prime. So I'm setting a prime greater than 0. And when I do that and I solve, I end up with x is less than 81. So I get x is a less than, the constants and everything on there. Okay, now we need to test the other side. So we want to know when f prime is less than 0, we need to know that x is greater than all the c's. So very similarly, we have 162 minus 2x is less than 0. When I go ahead and solve that, I end up with 81 is less than x. And that's exactly what we wanted. We wanted the x to be bigger than the constant. All right, now that we've shown that we definitely have a maximum value, an extreme maximum on this interval, we can, or for this function, we can go ahead and assume that when I set a prime equal to 0, that it is indeed that maximum area. So we have 162 minus 2x equal to 0. If I go ahead and I solve that, I get x equals 81. And since this, if I plug this x back into, so we know what x is, I need to solve for y. So if I go ahead and I go back up to the y equation, which is this one right up here, and I plug 81 into that for x, I end up getting 81 for y. And that's no surprise because as we've already discussed, we expected this to be a square. So we know this is an 81 by 81 rectangle. And it would have a maximum area of 6,561 centimeters squared. All right, so those two problems were easy enough, especially since we already kind of knew that we were going to be looking at a square when we were done. So the question is, what happens when we aren't dealing with a square? And where does that even come into play? And honestly, probably more often than not. So if you read this next problem, we have a farmer. He's got fencing, and yes, this is all debatable. We have this river running along here, and so we don't need any fence on this side. We only need the fence to go here, here, and here. And so I'm going to call these two sides x and this side y. Now, we know how much fencing we have, so that's a perimeter problem, because fence would go around it, but this is not your standard perimeter because we're missing a y. We don't need the side where the river is. So we have two x's and we have only one y. And we know that that's 2,400 feet. So we know that perimeter function will be set equal to 2,400 feet. Now we're trying to get the largest possible area. So we're trying to maximize the area, and the area in this case is still x times y. All right, again, we want this in terms of x's, so we're going to have y equals 2,400 minus 2x. We're going to go ahead and substitute this in for y. And when we do that, we get x times 2,400 minus 2x. And I'm going to go ahead and distribute the x because, again, I don't want to do the product rule whenever possible. So we've got 2x squared. We've got 2,400x minus 2x squared. All right, we could go ahead and verify that we can use the first derivative test, but because this is a rectangle and it's a similar situation to one we did before, it'll fall under the same category, so we do have a maximum value here. I'm going to go ahead and do a prime of x. So we would have 2,400 minus 4x. And if I want to set a prime of x equal to 0, I can do that simply by saying 0 equals 2,400 minus 4x. So 4x equals 2,400. And if I go ahead and I divide that out, I get x equals 600 feet. So the x is equal to 600 feet, but unlike the previous problems, that does not necessarily mean that y equals 600 feet. So if I go ahead and I plug x back into the y function here, and I go ahead and solve for it, I actually get y to equal 1,200 feet. So we were asked to find the dimensions, so our final answer can be 600 feet by 1,200 feet. And if we wanted to go a step further and actually say what the actual area is, which we were also asked to do, we would have 720,000 feet squared. All right, we have a good old open box top problem because, again, if this didn't have an open top, it'd be a very simple process because we know it would be a cube, similar to the square problem. So we have this box. We only know that this base is a square. And that was a really pathetic square. But the base is a square, and it has, we don't know what the height is. We aren't told what the height is. But we are told the amount of material that was used to make the box. So right now we have 6 sides, but one of the sides is not being occupied with the material because it has an open top. So we need to actually find the area of 5 of the sides. All right, so the front of the box would have an area of XH, because this is X and this is H, so we multiply those two together. Likewise, this would also have an area of XH, so would the left side and the back side. So we actually have 4 XH's involved in this surface area problem. And then we have this base down here, and that base is X by X, so we have plus an X squared, and that would be our surface area. And in this case, we know the surface area equals 600. All right, so the volume for the box is just going to be the area of the base, which we know is x squared, times the height, which we don't know. And again, we have the same problem we've had. We have to have this in terms of x. There's an h in the volume, so we're first going to have to solve for h over here and then plug it in. So if I do that, I get 4xh equals 600 minus x squared. And I'm going to go ahead and divide by the 4x to get me a height expression in terms of x of 600x minus x squared over 4x. And now I'm ready to go ahead and put that in to my height in the volume function. So I will have x squared, and this will be times 600 minus x squared over 4x. And now, hopefully you notice some things, like this x here can reduce with one of those x's. And then I can also distribute the x to both terms inside and divide each term by 4. I know how much you guys hate it when I do too much at once, so I'm not going to do it all at once. We'll do it one at a time. So this would be 600x minus x cubed over 4. And now I'm going to go ahead and distribute the 4 to both things. So I would have 150x minus x cubed over 4. And again, the reason that I did that is that I don't like to have to do the quotient rule and the product rule unless I absolutely have to. And I like logarithmic differentiation, but I'd rather not use it on a simple problem if I don't have to. All right, it is time for us to go ahead and take our derivative of the volume. So if we want to find this maximum value, the largest possible volume. So if I do that, I get 150 minus 3x squared over 4. And I want to set that equal to 0 as in past problems. And if I do that, I get 150 equals 3x squared over 4. Multiply both sides by 4. And divide by 3. I end up with 200 equals x squared. So now I need to go ahead and square root that. And if I square root that, I know that that is 100 times 2, or 10 square roots of 2. Now I'm supposed to find the largest possible volume. So now that I know the x dimension, I don't actually have to go figure out what the y dimension would be for this case. I just have to find the largest possible volume. And my volume that I found before I did the derivative, my volume function that I found before I took the derivative, is this guy right here. It's all in terms of x, so I don't have to find the height. I just have to find the volume of 10 square roots of 2. So I just plug in 10 square roots of 2 in both these spots, and I let my calculator do the work for me, and I got about 1,414 centimeters cubed. All right, we'll do some more tomorrow. Good luck on your homework.